Here are solutions to homework set number 6 for ECE 341. Now the first problem is scale this so this is a valid PDF. For a valid PDF, the area has to be 1. So what I can do is calculate the total area as drawn. So the area of a triangle is 1/2 base times height. So that's 1/2, 2 times 1. So this has an area of 1. This area is 0.2 times 3, 0.6. So the total area is 1.6. That makes this an invalid PDF. So if I take the x-axis and scale it by 1 over 1.6, now the area is 1 and it's a valid PDF. So I've got to scale this by 1 over 1.6. I can then represent this as a function. So for x less than 0, this is 0. For x between 0 and 2, this is 1 over 1.6, and the slope of the line is change of 1 in 2 seconds, 1/2. Times your scalar between 0 and 2. 0 between 2 and 3, and 0.2 times your scalar between 3 and 6. So there's your PDF. The cumulative distribution function, or CDF, is the integral. So if I integrate that, the integral of 0 is 0. Integral of 0.3125x is 1/2 0.3125x squared plus a constant. And what the constant does is it has to be continuous. So for x less than 0, I'm at 0. At 0, I've got to be at 0. So plug in 0, I know the answer is 0 at 0. And you get c equals 0. And that takes you to here, to 2. The integral of 0 is a constant. And it's got to match up right here. So if I plug in 2 in the previous part, 2 becomes 4. Let's cheat. Becomes 0.625. That's the constant between 2 and 3. And now the integral of 0.125 is 0.125t, or 0.125x, plus a constant. What that constant does is it makes it a continuous function. Has to match up at 3. So plug in x equals 3, I've got to get 0.625, and that constant is 0.25. And then at 6, the integral of 0 is 0 plus a constant. Pick the constant to match up right here, and it turns out that constant is 1. So here is the CDF. Given x, this is the total probability, the total area to the left. And in MATLAB, I can program that. I'm going to type in x and just use a bunch of if statements. If x is less than 0, then the probability is 0. If x is less than 2 and bigger than 0, here's the probability. Else, if x is less than 3, is a constant. Else, if x is between 3 and 6, there's a constant. Else, if x is bigger than 6, the probability is 1. And to check, what I can do is have x sweep from -1 to +8, calculate the probability at each point, then plot it. And here's what you get. So this is the CDF, this is the total area to the left. And as a check, it's got to be 1. It's got to wind up at 1 and start at 0. Problem 3. Using that, find 20 random variables of x from the above PDF. Now there's a couple ways of doing that. You can sit there and take the inverse function, given x, find p, given p, find x. That's a valid solution. Another way is to use numerical methods. So I'm going to kind of show you 2 different numerical methods. If I can find MATLAB. So the first one, where am I? Come back. Nope. You stay there. You come down. There. The first approach is I'm going to use the CDF to try to find, well, given P, find the X value that corresponds to it. So one approach is to start at 0 and start sweeping to the right and find the first point where the probability is bigger than what I passed. And that's what this routine does. I'm going to plot, just for fun, this function. So X goes from 0 to 7, kind of guessing on the range. At each point, calculate the probability corresponding to X and then plot them. To solve for X as a function of P, I'm going to start at X equals 0, then sweep to the right. As long as the probability of the CDF is less than P, I'll keep on sweeping to the right, plot it, and pause. That slows it down, but it's kind of fun to watch. And here's what it looks like. In MATLAB then, let's pull this down so you can see. If I say, what is PDF1 0.2? I'll start at 0 and sweep right until the CDF is bigger than 0.2. And I'm stepping 0.1 every time. As soon as I get there, there's the answer. X is 1.14. Let's try 0.4. And it starts at 0, sweeps right, takes it a while. There's your answer. If I take out the print commands, it'll be faster. Let's try 0.8 then. So, searching. Where is the CDF bigger than 0.8? If you take out the prints and the pause, it runs faster. But this kind of shows off what's happening. And eventually, poop, there's the answer. X is 4.4. And it can go faster if I take out these two commands. There, a whole lot faster. That's one approach. This isn't a very efficient search algorithm. A better one would be interval halving. With interval halving, what I do is I guess the two endpoints. I think the solution is going to be between 0 and 10. Then take the midpoint. If at the midpoint I'm above P, replace the right endpoint. If I'm below P, replace the left endpoint. Repeat 20 times. So, kind of show you how that happens, how that works. If I say PDF of 0.2, my first midpoint is 5, 2.5, 1.25, and that was kind of quick. Let's slow that down. Yeah, I lost it. So let's pause 1 second. This could be too long. 0.5 seconds. The other 0.5 seconds. So I try 5, 2.5, 1.25, keep on dividing by 2, and eventually I iterate and find the solution. What's nice is this only took 20 iterations to get the answer and to get better resolution. The previous method I was only good to 0.01, and this is 1/2 to the 20th power is how good the resolution is. If I try another number like 0.4, can go through the same algorithm. I try 5, 2.5, 1.25. Keep on replacing the two endpoints 20 times, then I kick out. If I try 0.8, there it is. That's interval halving. Third approach that we use in 111 is called Newton's method. Newton's method doesn't work very well here. With Newton's method, what I do is, let's go back over here. I'll take a guess and then draw a tangent to it. From the tangent, interpolate where the solution should be. That doesn't work real well because I have the splat area. If this is my guess, draw the tangent, I go out to infinity. So Newton's method doesn't work quite as well here. Instead, interval halving is probably the best way to go. But anyway, that's a numerical way to find the answer. Oops, come back. Erase, erase, erase. So doing that, what I can do is guess 20 random p's. From that, determine x that corresponds to that p. And if I do it, in this case I swept from the left to find it. The points lined up on the CDF, so that's good. And here's p, here's the corresponding x's. And notice there's no x's between 2 and 3 because this is flat. The PDF was 0 in that range. Or using interval halving. Now here's my function using interval halving. I keep on taking the midpoint between the two, keep iterating. With that, I can say generate 20 random probabilities, calculate the corresponding x using interval halving. And here's the p's on the left axis, corresponding x's on the y-axis. So that's what the CDF is good for. Given I can calculate x's that satisfy that PDF using the CDF. The last problem is find the Laplace transform, also known as the moment generating function, for x. So here the trick is take the derivative until I get delta functions. I like delta functions because I know what that Laplace transform is. It's 1 times the delay. In this case, well, the amplitude is 1/8. Delay 3 seconds minus 1/8. Delay 6 seconds. Take the derivative again. I turn the step into delta functions. I like delta functions because I know that Laplace transform. So this is, what's that, 3/8 minus 3/8, delay 2 seconds. Then to find the Laplace transform, or moment generating function, this got integrated once. This you have to integrate twice. And there's your Laplace transform. So that's homework set number 6.